Good morning, Gwen. Oh, that's okay.
It's blooded. I didn't see this every. Oh, you're right.
So while you're waiting, you can get your packet out. Someone needs to tell Mr. Austin it's not the 1990s anymore. Made some improvements in music. Good morning, Atticus.
That's just right here. Hey, I already had Mr. Hoskins. There are no other teachers.
In case you're wondering what the schedule for, you know, AP Cabinet is always a great decision. Good morning, Amanda. All right. So you can just look at this wonderful class while I hand out the papers. Or you can look at the. Or we'll make you guys sick by spinning the iPad around and around. There, you can stare at the desk. All right, let me just hand out some papers and we'll get going. If you want, but whenever there's an empty table, if you want to see it over, you get more space. After. Good morning, Kaylee. So, I was just gonna say, for you, so Amanda and, Wyatt and Addie, I came in early this morning to, videotape the next lab for you. And midway through the lab, the pressure gauge broke. So then I had to start over and did the lab again. And then midway through that one, the handle broke. So even though I came in, I apologize, even though I came in at 7:30 to videotape your lab, 2 times I had problems. So I'm gonna have to videotape the lab for you doing 5th hour and upload it. So I apologize. Atticus and Kayla, you guys can do the lab next week when you come back to school, okay? So today's agenda is we are going to finish the notes on pages, I think, 16, 17, like 16, 17, 18, and 19. And then depending on how long it takes us, we might either start the next lab or just have work time on our homework. It really kind of depends. But because we should get through all the notes today. Yeah, we're on 17. We'll get through 17, 18, and 19 today. All right. And just a reminder, as you're signing up for your classes, you want to make good decisions. Don't just sign up for classes with your friends, especially if your friends are distractions to you. And whatever you do, don't sign up for a class with your boyfriend or girlfriend. That's like guaranteed to cause a problem. Haley. All right, we ready? So yesterday, actually, I'm going to go back to yesterday's notes. So we went through what all the variables were. Oh, I'm not screen sharing. Sorry. Okay, so yesterday we went through all the variables, N, L, M sub L, M sub S. And we know that changing N changes the size, okay? So we graphed N equal to 1. Okay, we graphed N equal to 1. Actually, the graph is right here. N equal to 1, L equal to 0. So we graphed that data, okay? So what we're going to do now is we are going to change the variables and see what it does to the graph, okay? So we're going to do N equal to 1, L equal to 0, M sub L 0, and M sub S minus 1/2. So we're going to keep all the variables the same except for the spin. We're going to change the spin to negative 1/2, okay? So I'm going to do this one a little bit quickly. I'll slow down for the other ones. So we draw our axes. And if we take those 4 variables and we graph them, Lily, it's going to look like a sphere. We're going to do a cutaway. And then we're going to shade the skin of our sphere. So this is for an electron that's rotating in the opposite direction. So again, yesterday we graphed n equal to 1, L equal to 0, M sub L 0, M sub S plus 1/2. That's the graph we got. Now we're going to graph everything, but we're going to change the spin. So it's going to be rotating in the opposite direction. There's still 0% chance of finding the electron in the center. There is still 0% chance of finding the electron at infinity. And then there's a lesser chance on the inside. So the greatest probability is at 0.529 angstroms away. There's a 59% probability of finding the electron there. So the darker the blue, the higher the probability. The lighter the blue, the lower the probability. So you can find it outside the sphere, but the probability is less. That's why they are called fuzzy spheres. So like I said, I know I did that one a little bit quickly, but so did the graph change? So when you change the spin, Lilia, did our graph change at all? No. Okay. Now I told you that yesterday, so you probably knew that, like, oh yeah, Mr. Strauss said spin doesn't affect the graph at all. So why did I make you graph it if spin does not affect the graph at all? Well, here's the reason why. And just kind of point out one of the strange things about quantum mechanics. So if I have one electron and it's spinning clockwise, the most likely place to find it is 0.529 angstroms away. If I have another electron and it's spinning in the opposite direction, it too is most likely found 0.529 angstroms away. So here's one of the strange things about quantum mechanics, Allison, is if I have two electrons and they're spinning in opposite directions, the most likely place to find them is in the same place. Okay. So I'll say that again, see if it sinks in. If I have two electrons and they're spinning in opposite directions, the most likely place to find them is in the exact same place. How can that be? How can two objects occupy the same region of space at the same time? Okay, it's not like Charlie and Sanuja can occupy the same chair at the same time. It's impossible, right? Only one of you can fit in that space. But electrons, these two electrons can literally be in the same place at the same time. And the reason why that is because they're also waves, right? Two waves can be in the same place at the same time, can't they? Can two sound waves be in the same place at the same time? Yeah. So I just wanted to kind of point this out, like when you get to the quantum mechanical level, when you get really, really small, strange things happen. And this is one of them. Two objects can be in the same place at the same time. At our macroscopic world, that's impossible. Okay, you can't have two people sitting in the same chair. at the same time. So any questions at home before we move on to changing n? And I'll slow down for n. Okay, so for the next page here, we're going to change n equal to 2. We're going to keep the other variables the same. We're not going to do the spin because, as we just saw, the spin doesn't change the graph at all. Okay, so we're not going to do spin. We're just going to stick with the first 3 variables. So what does n change? The size of your graph. So our graph should be bigger. I'm going to draw the first graph. I'll have the second graph here. So the first graph looks like that. Yep. That's the first graph. This one's got negative values. What happens when you square a negative number? It becomes positive. So the second graph looks like that. The axes are still the same. This is percent probability. And this is still distance from nucleus. The first hump is 0.55 angstroms away. And the probability is 5%. So the first little hill is 0.55 angstroms away, and the probability is 5%. The second one is 2.3 angstroms away, and its probability is 19%. Yep, Sanuja.
How do you know the graph?
So that's the why question that we're avoiding. So like, how do you know that that's a circle? So Sanuja asked, how do I know to graph it like that? How do you know that that's equation's a circle? So all I can say is, like, if you take the equation and you put it in the calculator, or if you manually graph it, this is what it looks like. Similarly, if you take this equation and you put it into your calculator or you graph it, it gives you a circle. So that's unfortunately the best answer I can give you until you guys have calculus and radians. So I'm kind of skipping the why and saying, here's what the end result looks like. Here's what the graph looks like. So now I'm going to put it into 3 dimensions. So because I have 2 humps here, Simon, I'm gonna have 2 spheres, a sphere within a sphere. Okay, so 2 spheres. So I draw my first sphere. I cut away So I can look inside. And this first sphere has a radius of 2.3 angstroms, and the probability is 19%. Okay. Where's the other sphere? The other sphere is smaller. I'm going to cut away so you can look inside that one. And that sphere has a radius of 0.55 angstroms and a probability of 5%. Now, where are the nodes? Where is it 0%? Well, actually, I should use a different color. What color should I use? I think I'm going to be going with yellow. So at the origin, there's a 0% chance of finding the electron. At infinity, there's a 0% chance of finding the electron. Okay. I'm just going to take that line out of there. We'll stay color coded. So at the nucleus, there's no chance. So is it possible to find the electron right there? Is it possible to find the electron right there, Jaden? That little brown dot. Could I find the electron there? Yeah. So Jaden says yes. If the electron is on the outer sphere, what's the probability of finding the electron if it's on the outer sphere? 19%, right? What's the probability of finding the electron on the inner sphere? 5%. Now, the electron can be between those spheres, but the probability will be less. So I'm going to shade it in lighter. So you could find the electron inside the spheres and outside the spheres, but your probability is going to be less. Okay. So here's where another strange thing of quantum mechanics arises, and Zoran kind of alluded to it. There are 3 nodes, right? The origin, infinity, but it dips in between. So there is a node in the middle there. In other words, there's a 0% chance of finding the electron in that spot. Okay, you can't find it there. Okay. It's like the probability of finding me at a bridal shower. Percentage is 0. Ever go to a bridal shower? No, neither have I. 0% chance of finding me there. Okay. So, Amanda, I want you to think about this for a second. All right. Can the electron be right there? Can the electron be there? Okay, good. Can the electron be there? Okay, so how does the electron go from here to there without going through that space in between? Because if the electron has to go through that space, through that yellow region, then there should be a chance of finding it there, right? If you're saying like, I'm gonna walk down the hallway from one room to the other, there should be a chance then of finding you in the hallway. But quantum mechanics says that it's impossible to find the electron in that yellow region. Somehow electrons are able to tunnel through space. In other words, they could go from one room to the other room without walking down the hallway. Somehow they disappear and reappear in another location. We can't do that, Nancy, Muncie. Combined your names, Nate and Muncie. So we can't do that, but electrons can. So there's another strange thing about quantum mechanics is that they can tunnel through space, we cannot. But then the question is, why can they and why can't we? Because they have mass, right? We have mass. So if they can do it, why can't we? All right, so what does this look like? There is what we just drew, n equal to 2. A sphere within a sphere. The black, I think in this one, actually, the white regions are the node. No, the black regions are the node. Okay, so we drew n equal to 2. Now we're going to change L. So what does changing L do? If you change the angular momentum, here my angular momentum is 0, we're going to change it to 1. N changes the size. What does L do? What does it change? The shape, okay? Now, this one's it's going to be less painful than the others, okay? We're going to do all the rest of the graphs at the same time, okay? So we're going to do all the remaining graphs together at the same time. They all look the same. That's why we're doing them all at the same time. Saves us some time. I'm just going to go ahead and draw in my axes, my three-dimensional axes. And then I'll wait for everybody to catch up. All right, so when we change L, it's going to change from a sphere to what some people call is like a dumbbell or a bow tie or something like that. I kind of think of them as two distorted ellipses. And if we cut away the inside, they're hollow, just like the sphere. So you can just think of them as two distorted spheres, one above and one below. And there's a probability of finding it on the inside. Oop. And there's probability of finding it on the outside. So it changes from a sphere mic to, I don't know, a dumbbell, figure 8. We call these the p orbitals. And because it's on the z-axis, we call it the pz. Okay. The other two look the same way, Jordan, except they're not on the z-axis. Okay. So changing L changed the shape. Changing M sub L changes the location of the graph. So the next two graphs look identical, except that they are found on different axes. So this one is on the math and science don't agree on what these are called. I believe this is the y-axis and this is the x-axis. It doesn't actually matter how you label them. There's 3 of them, one on the z. Oh, that's the one. This is the one they disagree with. In math class, I think they call that the y-axis. In science, that's the z-axis. Again, math and science fighting. So there's 3 of them, px, py, pz. They're on different axes. Okay. And then usually the question is, what the heck did we just draw? Okay, so I just want to remind you that these are called orbitals. And you're going to hear that word used a lot, okay, over the next 2 weeks. And I'm going to scroll back to this page right here, page 16. In bold, it says the definition of an orbital. An orbital is a probability graph of where you might find an object, okay? So an orbital is a probability graph. What's an orbit? An orbit is an exact path. So the moon orbits around the Earth, right? Do we ever not know where the moon is? Are we ever guessing? No, right? The moon takes an exact path. The moon orbits. The electron, we know it goes around the nucleus, but we don't know where it is. So we can't really say the electron is orbiting if you can't find it, because we don't know the path the electron is taking. The best we can do is come up with a probability graph. So it is not like the electron is doing this. So the electron's not doing a figure 8 orbit. all I can say is right here, there's a certain chance of finding it. Right here, there's a certain chance of finding it. Right here, I'm not going to find it. Probability is 0. Okay. Same thing up here. It's not like the electron is going round and round and round and round. No. All I can say is right there, there's a chance of finding it. Right here, there's a chance of finding it. Right there in the node, no chance. Okay, that's all we can do. And because of that, that's why Einstein didn't like quantum mechanics. He said this is all kind of like guesswork. And yeah, he's kind of right. It is kind of guesswork. We're doing probability. So, and there are still some problems with quantum mechanics. So perhaps Einstein will be right after all. Because I would like to watch one more video, but we're not going to do it till next week. So whenever you get confused or you start to like lose focus, just tell yourself it's a graph of probability. Okay. So at this point, in Canvas, you guys in the classroom don't have to go into Canvas because I gave you the handout. But for those of you at home, you're going to want to go into quantum mechanics, and there's a sheet called Orbital Handout. So I would import that into Notability. I mean, you guys can do that too. If you want to take your notes in Notability, you can import it into Notability. But you should have that diagram. Okay. So all we're going to do now is kind of summarize everything we've learned. So when L equals 0, I need to import this to Notability. So this is kind of where I was talking about before, like you can do quantum mechanics without understanding quantum mechanics. It didn't show up. There it is. All right. So when L is 0, we get the s orbital. Okay, so when L is 0, you get an s orbital. Its shape is a sphere. When we changed L to 1, what happened? Our sphere split into 2, and we ended up with p orbitals. And we ended up with 3 of them. Now, we're not going to draw these other graphs. That's why I gave you this handout. When L equals 2, we end up with 4-leaf clovers. And when L equals 3, we get double 4-leaf clovers. We're not going to draw them because we'd have to draw, well, how many would we have to draw? Someone said a lot. How many S's are there? How many P's are there? Don't write these numbers down because we're going to write other stuff under there. How many D's are there? How many F's do you think there are? 7. 1, 3, 5, 7. Where have I heard those numbers before? when we did that, and I don't know where it went, maybe it's over here. On page on page 8 of your notes. I don't know where it is, but if you look on page 8 of your notes, you'll see the spectral lines. And the spectral lines go 1, 3, 5, 7. So the quantum mechanical model, the Schrodinger model, is responsible for those that pattern we saw on page 8 of your notes, the 1, 1, 3, 1, 3, 5, 1, 3, 5, 7. M sub L goes from L to negative L. So the value of M sub L, M subscript L, goes from L to negative L. So the way this works here, Amanda, is we take this value and we plug it in. So if my L is 0, my M subscript L must be 0. You see that, Nathan? I took 0 and I plugged it in right there, right? So in other words, M subscript L will be from 0 to 0. But when L equals 1, now M subscript L equals 1 to negative 1. We end up with 3 values. And when L is equal to 3, whoops, sorry. When it's 2, and then for the F orbital, M sub L would be 3, 2, 1, 0, negative 1, negative 2, negative 3. So this is a good handout to study from. The reason why that's called the S orbital is because it creates the sharp line. The reason why that's called the P orbital is because it creates the principal line. That's the D because it is responsible for the diffuse line, and it's the F because it does the fine line. You change L, you change the shape. It turns from a sphere to a dumbbell. You change L again, it turns into a 4-leaf clover. You change L again, double 4-leaf clover. What happens when you change M sub L? Changes the orientation, which axis it's on. Okay. So what questions do you have before we summarize these in our notebook? Or in our notes? And again, if you're confused, like what the heck is all this stuff? These are graphs of where you might find the electron, okay? Graphs of where you might find the electron or not find the electron. It is complicated. That's why we didn't teach it to you in middle school. It's complicated in high school. But the reason why we teach it to you in high school is because this explains everything in quantum mechanics. So these last two pages of notes are the two most important pages. Because this is where basically we put, oh, that's 19. We don't want 19. Okay, so this is where we're going to summarize everything. So the principal energy level is N, right? N can go from 1 to infinity, but we're going to stop at 4. The number of sublevels equals the principal energy level. So if N equals 1, there is one sublevel. The only thing that is present is the S. What is the angular value for an S orbital? 0. So understanding the Y is great, but you could just memorize the heck out of this and still be fine. What's the angular value of an S? 0. Second energy level, 2 sublevels. Now we have the S and the P. The values are now 0 and 1. 3 sublevels, S, P, D. L now becomes 0, 1, and 2. And then the fourth energy level, S, P, D, F. And the values become 0, 1, 2, and 3. We doing okay at home, you guys? I know this is a lot. I think what we'll do today is probably just give you time to work on your homework. All right. An S is always 0. A P is always 1. A D is always 2. And an F is always 3. No, I think we can do the lab. We'll do the lab. Number of orbitals. So there's only one S. How many P's did we draw? 3. 5 D's, 7 F's. What does an S look like? A sphere, right? And M sub L has to be 0. What did the P's look like? Dumbbells, and their values were 1, 0, and -1. The D's, 4-leaf clovers, their M sub L's were 2, 1, 0, -1, -2. And you can Google online what the F orbitals look like. They look like a 4-leaf clover stacked on a 4-leaf clover, like a double 4-leaf clover. So a double 4-leaf. And their M sub L values go 3, 2, 1, 0, -1, -2, -3. So when you're studying for this test in another week, it won't be next week, it'll probably be the following week. As you can see, we're like almost done with notes, so now it's just gonna be doing and practicing. This is page 18 is a good place to come back to study because it's got everything organized for you, okay? For a specific energy level, you superimpose all the graphs together. We're not gonna draw this, but try to imagine drawing all 4 of those graphs on the same set of axes. If we were to do that, it would tell us the probability of finding the electron in the energy level n equals 2. So for any one energy level, you superimpose all the graphs together on one set of axes. But we're not going to draw that. Just imagine them all. Okay, Addie, just imagine them all on one graph. Are you doing it? Are you imagining? All right, last page. Because 2 electrons can occupy the same space at the same time, each orbital graph can hold up to 2 electrons, okay? Because 2 things can occupy the same space at the same time, Charlie, each orbital graph can represent 2 electrons. The maximum number of electrons that can be placed into an energy level is 2n squared. The total number of orbitals is n squared. The maximum number of electrons is 2n squared. I get kind of excited at this point, Elise. So the total number of orbitals is, in the first energy level, is 1. Maximum number of electrons is 2. 2 squared would be 4. Maximum number of electrons, 8. N equal to 3. Total number of orbitals, 9. Maximum number of electrons, 18. So I'll come back to the screen, but this is what we've been working towards all quarter. I'm gonna have Isaac videotape me here. So how many electrons can go in the first energy level? What's the maximum number of electrons that can go in the first energy level? 2. First row, how many elements? 1, 2. How many electrons can go in the second energy level? 8. Second row, 1, 2, 3, 4, 5, 6, 7, 8. How many can go in the third energy level? 18. Third energy level, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Coincidence? I think not. So the quantum mechanical model explains the periodic table. And although it's hard to understand, it is the basis of chemistry. So we have to teach it to you. And now that you understand it, or now that you've learned it, it'll take a while to understand it. We now can explain any question you have. So if you want to know why it's H2O instead of H3O, I can explain it. Or why does oxygen have a -2 charge instead of a -3 charge? I can explain it. because you will now know enough to explain the behavior of electrons, okay? All right, so how are you gonna do your homework tonight? There is a sheet that looks like this in your packet. Okay. This is such a good sheet. I gave you 2 of them. So that in case you lose one, you can have another. At home, you can print, well, you should have a packet at home, but you can also print this off. I put this into Canvas in case you want to print out more of them. So think of this, think of the periodic table as a bookshelf. And you're going to put books on the shelf, Allison. Now, if you're going to put books on the shelf, you don't start at the top shelf, you start at the bottom shelf. So I would use pencil because you're going to want to use this template a lot. So electrons are represented by arrows. Whoops, that's not an arrow. They're represented by half arrows. This is an arrow. They're represented by half arrows. Okay. So we are going to first do the electron configuration for hydrogen. How many electrons does hydrogen have? 1 electron. Remember, the number of electrons is the same as the atomic number. So if hydrogen is atomic number 1, then it's going to have 1 electron. I'm going to put it in the lowest available orbital. So these boxes are basically orbitals. Think of it as a bookshelf, Reese, and we're going to fill in the bookshelf. You start at the bottom. The electron configuration, Atticus, tells me where the electron is. So it's the first energy level. It is the S sublevel. Put that one, write it in black. And then how many electrons did we draw in? 1. So the first number is the energy level. The letter is the sublevel. And the superscript is the number of electrons. This is called the electron configuration. Let's do it for helium. So you have to start all over. That's why I said use pencil. That's why I gave you 2 of them. So if you messed up on this one, you can always use this second one. How many electrons, Wyatt, does helium have? 2, right? It's the second element, 2 electrons. Each orbital can hold 2 electrons as long as they are spinning in opposite directions. So I would put both electrons in that box as long as they have opposite spins. So then my configuration would be, they're in the first energy level, they're in the S sublevel, but now I have 2 electrons. So the configuration for helium is 1s2. What questions do you have before we do nitrogen? You okay, Kaylee? You ready for nitrogen? All right, nitrogen is element number 7. It has 7 electrons. You start all over. You fill the lowest box first. I can put 2 there. Now that that one is filled, the arrow tells me to go to the 2s, and I can put 2 of them there. After I fill the 2s, I'm going to fill the 2p. Now, on our note sheet, let's scroll down here. I'm just explaining rules 1, 2, and 3 is what I'm doing. Okay, I didn't refer to them on the note sheet, but that's what I'm doing. So the rules are there for you, Jordan, if you want to go back and read the rules. But we've done rule number 1. We've done rule number 2. We are on rule number 3. When electrons are added to orbitals of equal energy, a single electron must enter before another one may. Spins must remain parallel. So this is called like the putting kids in the bedroom rule. If you have 3 children, Hannah, and 3 bedrooms, you put all 3 kids in one bedroom? No, you give each kid their own room, right? Before you start to double them up. So I have got 3 more electrons here. I'm going to put 1 in each box before I double them up. Okay? The spins have to be parallel. So they're all spin up or they're all spin down. It doesn't matter, but their spins must be parallel. Okay? So then the configuration would be 1s2, 2s2, 2p. How many electrons did I draw on the p? 3. So 2p, 3. So that's the electron configuration. This is what you have to be able to do on the test. So it's like all those graphs and things, you don't have to draw those on the test. This is what you need to be able to do. You need to be able to do configurations in your sleep. Now, I probably could have just skipped to the last page here and just taught you this, but then you'd have no clue about what SPD and F and all that stuff mean. Maybe you still don't, but at least you have a little bit better of a clue. Okay, so your homework, and then I'm going to give you time to work on your homework, is orbital worksheet number 1. Whoa. Where did everything go? Homework is orbital worksheet number 1 and study guide 5.2. So there are 2 worksheets that are due on Tuesday morning. Okay. They will go quick because I divided this chapter up into the math portion and the theory portion. So the theory portion doesn't have any math problems. So it will go a lot quicker for you when you don't have to do math problems. That's why some people like the theory better than the math and vice versa. So orbital worksheet number 1 and study guide 5.2. Study guide 5.2 is self-explanatory. You're just filling in the blank. Basically, look at pages 18 and 19 of your notes. Actually, I'd say look at pages 14 through 19 of your notes. Okay. to answer study guide 5.2. Orbital worksheet number 1. Question, Sanuja?
Is it the orbital diagram worksheet?
Yeah, orbital diagram worksheet number 1. I do want to do a couple of these on this worksheet just to get you going, okay? Just to make sure you're doing it right. And you might want to use that template as you do this. So let's do number 4 together, okay? So beryllium has 4 electrons. And you have to fill them up starting at the lowest orbital. So 4 electrons, I would be 1, 2, 3, 4. Right? So for beryllium, it'd be 1, 2, 3, 4. Beryllium has 4 electrons. Fill the 1s, then go fill the 2s. So each orbital can hold 2. So I go 1, 2, 3, 4. Okay. So see how this diagram is vertical? Okay, this diagram is vertical. On the worksheet, the diagram is horizontal. So I would go 1, 2, 3, 4. And then I write the configuration up here, 1s2, 2s2. Okay, so your homework is to just do that. Maybe we should just do boron together. Boron has 5 electrons, right? So I want to use this template. So I got 5 electrons here, Addison. 1, 2, 3, 4. Now I have 3 rooms to choose from. All 3 rooms are identical. So if all 3 bedrooms are identical, it doesn't matter which bedroom that electron goes in. Okay? You can put it in any one of the bedrooms there, Mike, because all 3 bedrooms are identical. And also, when the electron is by itself like that, it can be spin down, it can be spin up. It doesn't matter. In fact, the electron spends 50% of its time in the spin down state and 50% of its time in the spin up state. So you could write it spin down, you could write it spin up. It doesn't matter. Only when they're in the same box does one have to be up and one have to be down. That's another reason why sometimes people like quantum mechanics, is because there's multiple possible correct answers. And on the test, Alyssa, I just want one correct answer. You don't have to give me all the possible correct answers. Just one correct answer is good. So this would be 1, 2, 3, 4, and then now I put one in the P. It could be up it could be down. It doesn't matter. Okay? I just always kind of like to start with up. 2P1. Okay? So I know that took a little bit longer than I expected, but so the last however many minutes of class, you have time to work on the homework. If you want to do it over the weekend, that's up to you. I'll let you, you guys have been a very good class. You can use the rest of this time as you see fit. If you want to work on the homework, great. If you don't want to work on the homework, that's fine too. Remember, if you have questions, you can always email me. This Monday, however, I've got science interviews in the afternoon, so I'm not going to have any office hours this Monday because I've got science interviews. So you Zoomies, I will stay on the chat room if you've got questions. Otherwise, if you want to log off, that's up to you. Boy, that didn't take them fast to log off.